welcome everyone. So today we are very glad to invite the Dr. Alice from Greece. He's going to talk about the lunar impact phase observation by his telescope in the project called NELIOTA. And I think he graduated, he got a PhD in 2012 in Greece, and now he's the postdoc there. So he has a very fruitful experience for the last 5 dictations. So let's welcome to Alice for this talk. Oh, sorry. So if you have a question, but please you can raise your hand or type the question in the chat box. Okay, let's welcome.
Hello to everyone. My name is Alexios Liakos. I am affiliated with the National Observatory of Athens in Greece, and I am representing the NELIOTA team. First of all, I would like to thank the Taiwan Space Union for the kind invitation. Today, I will present the long-term monitoring campaign for lunar impact flashes using the largest telescope in the world dedicated to this kind of observations. Before I get into details about the project, I would like to inform you that the first topographic lunar map was drawn by Julius Schmidt in 1878 as the director of the National Observatory of Athens using a small telescope at Theseion near the city center of Athens. As you can see in the screen, this is the historical building of the National Observatory of Athens that is very close to Acropolis. So, after 140 years, National Observatory of Athens, carrying this heavy heritage, again pioneers in the topic of lunar studies by dedicating a large aperture telescope for lunar observations. As already mentioned, this telescope is the largest worldwide for this kind of observations. The question that NELIOTA has been trying to answer concerns the frequency of the meteoroids with sizes of a few centimeters up to a few decimeters that correspond to masses between a few grams and a few kilograms. The works of Brown 2013 and Sachs 2014, as you can see from the plots, stated exactly our ignorance for this size range of meteoroids. The meteoroids of this size pose potential threat mostly to our satellites and space missions, as well as for the humans and infrastructure on Moon in the near future when lunar bases are going to be established. One plausible question is why we chose Moon for this kind of study while we could alternatively study the meteors on Earth. The reasons for this concern the small area coverage that we can cover using ground-based equipment, observing only the meteors from one side. Moreover, small-sized meteoroids are instantly burnt when entering the atmosphere, so they are very difficult to be detected. On the other hand, Moon lacks an atmosphere. Therefore, anything that falls on the lunar surface creates an impact. Impact means that part of the kinetic energy of the projectile converts to luminous energy, which in turn is a flash. Flash is optical and infrared radiation mostly and can be recorded using a telescope on Earth. Finally, Moon has a large effective area, which is more or less 19 million square kilometers, and I am referring only to the side facing Earth. NELIOTA is the acronym of the words Near Earth Objects, Lunar Impacts, and Optical Transient. It is a collaboration between European Space Agency and National Observatory of Athens in the framework of the Space Situational Awareness Program of ESA. Dr. Alkis Tibonanos is the BI of the project from the Greek side. Dr. Detlef Kosny was the science officer of the program until December 2022. Dr. Richard Moisel has been the technical officer from the ESA side for the last 5-6 years. The project began on early 2015, and the first 1.5 years was spent for the telescope's upgrade and the software development. This period was followed by a 6-month testing period, while on February 2021, the campaign started officially. The first observing period lasted until January 2019, when the 2-year extension of the program began. The official observations of NELIOTA ended on January 2021, but we continued the observations while pending for another extension. Finally, the campaign started again officially on June 2021 and will last until mid-2023 with the NELIOTA team as a collaborator of the ESA Carmen project. NELIOTA has been running in the Crionary Observatory. The observatory is located at Southeast Europe and particularly at Corinthia at northern Peloponnese in Greece. It has an altitude of approximately 930 meters and is approximately 120 kilometers west of Athens. It has 200 clear nights per year and it is accessible during all seasons. Although it can be considered as a bit old, it was established in 1972, it was completely upgraded in 2015 for the purposes of the NELIOTA project. For the needs of the project, we employ the 1.2 meter Crionary telescope and a twin camera system. Its camera is equipped with a different photometric filter, and particularly we observe in red and infrared bands simultaneously. The cameras have a synchronization accuracy of 6 milliseconds and a readout time of 10 milliseconds in 2x2 binning mode using global shutter. A 36 terabyte storage capacity is available for storing the data. However, the oldest raw data are deleted when disks are full. The detections are saved elsewhere and the flashes are stored in another archive center. We have a timing accuracy of less than 1 millisecond using a GPS receiver. Finally, we have a meteor station for the weather monitoring. These figures show the schematics of the NELIOTA architecture. The first one on the left shows the observations subsystems, that is, the telescope, cameras, GPS, meteo, and storage. These systems are controlled by the observations software. The second part is the detection software that detects and stores the flashes. The first and second parts are located at the observatory's area. The third part is the archive center, that is our database, and it is located at National Observatory of Athens headquarters in Athens. The final part is the website that contains all the online information, and we will talk about it later. This plot shows the transmission curves of the red and eye filters as well as that of the dichroic. The black solid line denotes the quantum efficiency of the cameras. Solid red and gray lines denote the final efficiency of our system. The main goal of the project concerns the size-frequency distribution of meteoroids and small near-Earth objects in the vicinity of Earth. The statistics will supply the space industry with valuable information about the satellite and space mission shielding, as well as for future lunar bases establishment. Now, a few words about the strategy we've been following since the beginning of the campaign. We observe the non-sunlit side of the moon facing Earth, and particularly between 10 and 45% of illumination phases due to the glare of the day side, but I will talk later about it. That corresponds to 5 to 8 nights per month, while the observations of each night range between 20 minutes and 5 hours. The observations begin or stop when the moon is at an elevation between 10 to 18 degrees, as we will see in a later slide. The field of view for each observing period is shown on the right image. Our field of view is 16 by 14 arc minutes, and we cover a mean observable area of 3 million square kilometers of lunar surface. At this point, I would like to talk a bit about the glare, since it is the most preventing reason of lunar impact flash observations. Glare increases the background of the lunar surface and decreases significantly the contrast. Therefore, the emitted light of the flashes is literally drawn in the noise of the background. Regarding our system, we have determined that useful observations can be obtained up to 44 to 46% illumination phase of the moon. This small deviation is due to Earth-Moon distance. When Moon is closer to Earth, the pixel scale of the setup decreases. Therefore, less light is gathered on one pixel, which in turn produces lower increase of the background in comparison with the case when Moon is at longer distances. As you can see from the left image, sometimes we need to sacrifice observable lunar area in order to include less glare in our data images. Of course, the glare can be reduced by using refracting telescopes, but we lose info due to their smaller sizes. Now we will see some examples of the observation plans for the two observing periods of the moon in a given month. During the waxing phase, we begin the observations approximately 20 minutes after the sunset. We split the observing period into lunar and standard star chunks. Specifically, every 15 minutes, we observe a pre-selected standard star for magnitude calibration reasons. Finally, the observations stop when Moon reaches an elevation of approximately 10 degrees. During the waning phase, the plan is almost the same, but in reverse order. That is, we begin when Moon is approximately at 18 degrees of elevation due to dome preventing reasons, since the optical axis of the telescope is eccentric with respect to the dome center, and we stop the observations approximately 20 minutes before sunrise. For the purposes of the project, a dedicated software pipeline was developed. The software performs the image calibration of lunar images and calculates the lunar background using a time-weighted algorithm. The images that are closest in time to the currently inspected image have bigger weight. The software examines the pixel values of the difference image for exceeding a preset threshold. If a pixel or a group of pixels indeed exceeded it, then the software saves the specific image along with 7 frames before and 7 frames after the last detection. Moreover, it automatically saves the respective images from the other camera in the same directory. The evaluation of the events is made by visual inspection by the expert user. In this slide, you can see some example of detections. On the left side, you see a real flash. In the middle, you can see satellites crossing the field of view of the moon, and on the right side, cosmic ray hits. Flashes typically show star-like shapes, while cosmic rays produce, in general, more sharp shapes. The fast-moving satellites produce streaks and can be easily discarded. On the contrary, slow-moving satellites, like those that orbiting Earth at medium Earth orbit zones or geosynchronous orbits, appear almost still in the images, and they might create a false positive event. However, those that cross several pixels in the field of view create a time pattern of detections, and this is also easy to be checked by the user. The problem is with those that cross only a few pixels on the lunar surface. In addition, cosmic rays that hit perpendicularly the sensor might also create flash-like shapes, and they might also be wrongly identified as flashes. For the suspicious events that could be potentially be false positives by slow-moving satellites, we perform another check. We use the orbit information from UStratCam and GitHub and the SGP4 orbit propagator to calculate the orbits of the satellites. Then, using their equatorial coordinates and the master proof tool of ESA, we perform a statistical analysis for objects inside the field of view during the observations. In order to be honest, we have indeed detected some satellites that were false positives. Approximately 1 or 2% of our findings were attributed to slow-moving satellites. For the evaluation of the events, we have established two main criteria. The first concerns the detection in both cameras and in the same lunar area, and the second one concerns the no movement of the event between successive frames. Real events satisfy both criteria. For those that they don't, we have set various cases in order to characterize them. In case that both criteria are not satisfied, or the event has been detected in both cameras but it moves between successive frames, then these events are rejected. The last case, that is the detection in only one camera, has two subcases. The first concerns the detection only in R camera. For this case, based on the R- index of the validated flashes so far, we can easily see that there is no possibility to detect a flash only in red and not in I passbands, because the flashes are always brighter in the infrared band. Therefore, we directly reject also this case. The detection only in the infrared camera has also two subcases. If the event is a multi-frame one, then it is characterized as suspected flash of class 1. If it is a single frame flash, then we compare its full width at half maximum with those of the standards. If it's not inside the 2 sigma range, then it is rejected. Otherwise, it is characterized as suspected flash of class 2. For the validated and the suspected events, we apply the aperture photometry technique to measure the flux of the flash in each image. Finally, using the standard star observations and the Pogson formula, we are able to calculate the respective magnitude of the flashes in each band. For the localization of the events, we use a tool that is embedded in the same software. First, we provide the tool with a high-detailed lunar map exported by the Virtual Moon Atlas software. Subsequently, the user identifies the same lunar features in the map and the observed image and pairs them using its mouse. Finally, the tool exports the observed image with the mark on the flash's location. Finally, using again the Virtual Moon Atlas software, we convert the pixel coordinates to selenographic coordinates. Using this method, we have estimated an average error of half a degree in both longitude and latitude of the moon. After the completion of photometry and localization, the expert user has to update the database within 24 hours of observation. An external user can access this database and is able to see the information and snapshot of the flashes. Additionally, a registered user can also download the data locally using the Add to Cart tool and make his own analysis. The final dataset contains fitch cubes. Particularly, the first cube contains the original raw files of the event along with 7 frames before and after the detection. The second cube includes the automatically created background images. The third cube contains the difference images, that is the result of the subtraction of the calculated background image from the images that host the detections. Finally, regardless on which camera the detection was made, the software stores in the same directory the respective image from the other camera too, and of course, they are also available to the registered user. Now we will proceed with some sample of our data. On the left side, you see one of the brightest lunar impact flashes ever recorded by our setup. This flash had a peak magnitude of 6 magnitude in I band. In the lower panels, you see the successive frames. You can clearly see that the flash up to the third probably frame, slightly, very slightly in the fourth, and not at all in the fifth. Now we will watch a video of the most slow lunar impact flash ever recorded that lasted 12 frames, that is approximately 360 milliseconds. While the typical duration values of the flashes is 1-2 frames, that means less than 66 milliseconds. This is another sample of a multi-frame flash. In the first set of images, the flash is clearly shown in both cameras' frames. In the second set of images, the flash is still easily seen in the eye camera's frame, while it has been almost vanished in the respective R frame. Now, in the third frame of the same series, of course, the flash is detectable only in the infrared camera. Finally, in the fourth frame, the flash is almost vanished in the eye camera too. Using the sets where the flash was detected in both cameras and using the black body's law, we are able to calculate the temperature evolved in each set of frames and finally produce the temperature curve of the flash. Now we will watch another video. And you can see the flash on the upper left side. I will stop the video to explain. As the flash evolves, as you may see, two diagrams are forming. The upper one is the temperature versus time, which in other words is the cooling curve of the flash or the temperature curve of the flash. The lower diagram includes the light curve for each band. Finally, you may see again that after the fourth frame, the flash was recorded only in the I band because it became too cool, so it did not emit enough energy in the R band to be recorded as well. Now I will continue with the statistics of the campaign to date. So far, we have detected 176 validated flashes and approximately 100 more suspected flashes. All these detections were made in approximately 260 hours of total observations on Moon. This plot shows the statistics of the percentages during each month of the NELIOTA operations. Green columns denote the percentage of the observations time. Red columns correspond to the time lost due to bad weather conditions, and the orange ones to the time lost due to technical reasons. The pie plot on the bottom shows that the NELIOTA has observed approximately 40% of the total available time. These plots show the magnitude distribution of the flashes in the red and infrared passbands. Moreover, the distribution of the suspected flashes is overplotted in the I-band distribution. The reason for not having many validated flashes between 10 and 12 magnitude in the infrared band is probably due to their temperature. That means that they are not too cool to emit detectable light in the red passband too. In this slide, you see the map of the Moon where we show the positions of the NELIOTA detections to date. The crosses denote the validated flashes, while the filled circles denote the suspected ones, which are those, as I already mentioned, that were detected only in the infrared camera's frames. The latter ones, as you can see, are not negligible, and approximately 1 out of 3 flashes are characterized as suspected. Unfortunately, we cannot do anything more about them. Yellow symbols denote the sporadic flashes, while the others, those which were associated with active meteoroid streams during the time of observations. For the association of the flashes with active meteoroid streams, we use the method described in the papers of Madiedo et al. And Ortiz et al. In 2015. Briefly, we can say that we calculate the probability for a meteoroid that produced a flash to be part of an active meteoroid stream. Of course, as you can see from this equation, there are many parameters that are taken into account, but the details are given in these references. Briefly, we take into account the subradiant point of the Moon, that is the star in this image, and calculate the surface of the Moon that is perpendicular to the stream's flow. Then we calculate the surface included in the observing field of view, and using also other parameters from these equations, such as the zenithal hour rate of the stream, the time distance between the maximum of the stream and the timing of the flash, for example, and we check whether this probability is more than 40 or 50%. Now we will talk about the physical parameters calculation of the meteoroids. In this slide, you see a brief formalism we follow for calculating the parameter of the projectiles. The flux of the flash is based on the calculated magnitude of each band and is used for the derivation of the respective luminous energy. These energies are added together to derive the total luminous energy of the flash. Of course, there are two main critical parameters for which we have to make some assumptions in order to calculate the rest of them. The first one is the most important one and is called luminous efficiency, and its symbol is the letter eta. Luminous efficiency is the ratio of the luminous over the kinetic energy and has been estimated from meteor showers on Earth and meteoroid impacts on Moon during meteoroid streams. The second parameter for which we have to make assumptions is the velocity of the meteoroids, which is accurate enough only for those that are connected to a stream, while that of sporadics has a wider range. As mentioned before, due to the readout time of the CMOS cameras we use, we lose approximately 33% of the observations. However, in case of multi-frame flashes, we have developed a method to calculate the lost energy during the readout times. Particularly, we apply an exponential fit to the observed data points and calculate the energy lost during the readout by interpolation. Then, the amount of the lost energies is added to the measured energies, and then we follow the previous formalism. This diagram concerns the correlation between the emitted energy in red and infrared bands of the validated flashes only. Using this derived relation, we can use it to roughly estimate the maximum value of the emitted energy in R band of the suspected flashes, and in turn to estimate the maximum values of other parameters such as mass and radius. This is the best we can do for the suspected flashes. As mentioned before, the luminous efficiency eta is one of the most critical parameters to calculate the physical parameters of the meteoroids. However, we use the value 1.5 times 10 to minus 3 as suggested from other researchers. And if we use this value, we see in this distribution plot that the meteoroids range from a few grams up to several hundred of grams. However, if we focus on the first 400 grams and remake the distribution, we can see that the majority of the projectiles weighed between a few tens up to few hundreds of grams, while the 63% of the meteoroids we have detected so far weighed less than 100 grams. Based on the pre-mentioned formalism and assuming densities according to the parent bodies, the radii distribution shows that the majority of the projectiles have radius less than 4 centimeters. Finally, the expected crater sizes are of the order of a few meters, so it is still very difficult to be directly observed by lunar orbiting missions such as Lunar Reconnaissance Orbiter in the past. The temperatures of the flashes, which is the great novelty of our projects, are calculated using the black bodies approximation and the flashes from the red and infrared bands. The majority of the flashes show temperatures, as you can see from the distribution plot, between 2000 and 4500 kelvins. The right diagram shows our try to correlate the peak temperature of the flashes and the masses of the projectile. If we think very, very simply, we believe that the bigger the size or the mass of the meteoroid, the bigger temperature will be involved. This is not exactly true, and although we try to find such a correlations, we found that there is no any obvious. However, this is probably connected to the material of the meteoroids, but also to the material of the impacted area, since the lunar surface is not homogeneous and differs from location to locations. Think, for example, maria, craters, rocky mountains, etc. Anyway, this is a result for a deeper study for astronomers, probably in combination with other scientists that are specialized in the topic of hypervelocity impacts. Using the calculated masses now and the magnitudes of each band of the validated flashes only, we managed to correlate these quantities and to derive an empirical relation for each band. So, using these empirical relations, anyone who performs lunar impact observations may estimate the mass of the impacting meteoroid by a simple magnitude calculation, as long as the red or the infrared passbands are used. These relations could be quite useful for other lunar monitor systems, for example, those with one telescope and one camera. Now we will talk about the frequency, the appearance frequency of the meteoroids in the vicinity of the Earth. The table, as you can see on the left, includes the meteoroid impact frequencies on Moon. The upper value concerns the case we take into account only the sporadic ones, while the lower value is the frequency during the streams. When I say frequency during the streams, I mean a mean frequency, because each stream has a different zenithal hourly rate. So this must be calculated for every stream in order to be honest. However, a mean frequency rate is shown here for all the streams we have observed so far. Now, but you must also see clearly that this appearance rate is almost double when Earth-Moon system enter the streams. Now, if we extrapolate these frequencies on Earth, we can calculate the respective meteoroid flux rates for various distances from the Earth's surface for both normal periods of time or during the meteoroid streams. The diagram on the right shows the increase of the appearance rate as we move outwards the Earth limits, because, of course, the sphere we calculate this flux is getting bigger and bigger. At this point, I would like to remind you that these statistics can be used from the space industry for the satellite shielding and for future lunar bases establishment. Of course, there are also other groups that monitor lunar impact flashes. The most important ones is that of the NASA Meteoroid Environment Office that is located in Marshall Space Flight Center, and the MIDAS team of Dr. Madiedo from Spain. However, there are also other small groups from the States, France, Morocco, United Arab Emirates, and as I heard before a few minutes, also Taiwan has set up its own system. However, the common of this campaign concern the small size telescope use and the unfiltered or single band observations. None of this group has published online their results like NELIOTA does. The NASA group has announced 443 lunar impact flashes within a 15-year time period, but there are not any online details. Therefore, the detection rate you can see here was calculated based on one paper by Sachs et al. 2014, with the authors being members of the NASA Meteoroid Environmental Office. And that paper included a list of 126 flashes. The second rate you can see here is given by another team from the United States. Based on the findings of NELIOTA, we see that the detection rate has been at least doubled or tripled if we get into account the suspected flashes too. And furthermore, we detect 2 magnitude fainter flashes in comparison with the NASA team that corresponds approximately to 1 order of magnitude in less massive meteoroids. So far, there are 3 main works based on NELIOTA findings by the NELIOTA team. Of course, there are probably 1 or 2 other works that are based to our findings, but they are not parts of our team. I would like to highlight that the NELIOTA lunar map from the last paper was featured one of the 4 cover pages of the journal Astronomy and Astrophysics on January 2020. A new paper of our team is in preparation and is planned to be submitted after the official end of the project on June 2023. Of course, there will be also other observations of lunar impact flashes based on other systems. The most important one is the LUMIO space mission. LUMIO is a collaboration between ISA, Politecnico di Milano, and Technical University of Delft in the Netherlands, another university from Switzerland, Norway, Italy, and finally the University of Arizona. LUMIO is a CubeSat and will be located at the second Lagrangian point of the Earth-Moon system. It will perform full disk operations of the far side of the Moon when its illumination is less than 50%. LUMIO will have 2 cameras on a beam splitter and will observe in R and I bands with a frame rate of 15 frames per second. This setup is almost identical to the NELIOTA with the exception of the frame rate. LUMIO is expected to launch in the middle 2023, and you can find a relevant reference here and the website where you can seek for more information. Okay, now we'll return from the space to Earth, and I'm very glad to announce that our team, and particularly our former software engineer Stefanos Achlatis, has developed a software that is called Flash Detection Software on early 2023. This software targets also amateur and professional astronomers and can be used as a plugin to the far capture software. For those that are not familiar with far capture is a free downloadable software that is used mostly for planetary imaging. It can work with many telescopes and cameras, and our software, the flash detection software, is used as a plugin to that one. Our software, as well as the far capture, is free to download and use, and we encourage you to use it and send us your feedback. The software performs online and offline detection of lunar impact flashes, but if you have, let's say, stronger telescope, for example, larger aperture, you can use it for finding flashes also in another planet, for example, Jupiter, Saturn, or even Mars. With the yellow letters, you can see the link. You can visit and download this software. So again, we encourage you to download it, use it, and send us your feedback. Now, a few words about the future of our campaign. Unfortunately, the operations officially stop by the end of June 2023. However, collaborators of the Carmen project will continue the observations using smaller telescopes. Of course, we will not give up. We will seek for another funding probably on 2024, and we have plans for instruments upgrade, for example, more sensitive or more fast cameras. Of course, the most ambitious plan we have is to develop a database that will host the lunar impact flash detections from observers from all over the world in order to enrich our statistics and have more safe conclusions. I will leave you with some take-home notes. NELIOTA, as you can clearly understand, is to date the most efficient lunar impact flashes campaign. The meteoroids we have calculated, the parameters of the meteoroids we have calculated have typical masses of a few tenths of grams and sizes of a few centimeters. They produce typical temperatures between 2000 and 4500 kelvins. Moon is bombarded with a rate of 7.5 meteoroids per hour, while Earth with 100 meteoroids per hour at mesosphere and a little bit more when we're talking about Leo. Finally, on the lower right side, you can see the website of our project, which you can visit, register, or check other online details. Thank you very much for your attention, and I am open to your questions.
Okay, thank you, Alex, for that very fantastic speech. So, anyone, any idea? Do you have any question? Please raise your hands up or touch with the chat box. I can ask the question first. So, you may heard some the news from Japan that there's an amateur observe the one lunar impact flash in this year, and the duration is longer than 1 second. So my question is, from your experience, how the longest the one is something? Can you talk about this?
Yeah, the longest in duration flash we observed so far is
Yes.
approximately 360 milliseconds. That means approximately 1/3 of the second. However, except the flash you mentioned, there are also past papers that have flashes with durations 1 or 2 seconds, but they are extremely this is extreme values.
Okay.
The typical is less than 1 or 2 frames. It's less than 16 milliseconds. That's why in the beginning I proposed to you to use high frame rates.
Okay. My second question is, you mentioned the crater, the size of the crater is about 4 to 5 meter.
3 to 5, yeah.
Yeah. So I remember lunar resonance orbiter, the pixel resolution is something like 50 center per pixel. So why did they detect any crater from your
No, because we are because the expected crater sizes are less than this orbiter's resolution, so they cannot detect it. The one they detected was, I think, 50 meters or something like that. It was a large object. It was a small asteroid. It was not a meteoroid. That was they detected before a few years.
Okay. My next question is, how do we know the impact came from the spark article or string?
Sorry, can you repeat?
How do we know the impact came from SPO meteor shower or string meteor?
Yeah. That's a very, very good question. If you see in my presentation, we calculate the probability of a meteoroid impact to be associated with an active meteoroid stream. That means that we have to take into account, let's say, the strength of the meteor stream, but also the angle, the impacting angle of the stream on the moon in order to calculate this probability. So this is not a very easy task, and we can be certain only when we observe impacts during the maximum of the meteoroid streams, not during their whole periods. Because, for example, Perseids last approximately for 1 month in the sky. But the probability of impact to be associated with Perseids, let's say 10 days before their maximum, is almost zero. So you cannot distinguish them. But during the days of the maximum, let's say plus minus 1 day from the maximum of its meteoroid stream, this probability is getting much higher and reaches up to 70 or 80 or 90%. This is only a probability game. You cannot be certain because you need to take a sample and check that that came from that comet or from that asteroid. That is not a realistic scenario, of course.
Okay. So, any question from? Oh, okay. There's a question from Gin. Okay, please.
So hi, Alex. Thanks for the talk. This is SK. I'm interested in the glare effect you mentioned, and what kind of camera are you used for this kind of observation, and how can you improve that glare effect in your future plan? Thank you.
Yeah. Let me show you again the slide with the cameras. Okay, we use the Andor Zilla model is a CMOS camera, is a Zilla 5.5, I think. Here you are. Can you see it? These are the cameras, the two gray devices here. And they are connected through fiber to our server. Yes, you are right. They are not very sensitive, as you can see from this plot. Especially in I band, we have an efficiency of 30%, and in R band, nearly to 50%. Yes, we want to have better cameras. That means with better quantum efficiency. And in order to be honest, I would like to have cameras with that are most with higher frame rates, because we understand that the temperature calculation is a bit tricky, and it depends on the resolution, on the time resolution you have. We will have better estimation for the temperature evolution if we have more frames from the flashes.
So is that an EMCCD or is that CMOS design?
No. It's scientific CMOS. It's not an EMCCD, but that's a very, very good idea. I have already thought it. But the cost is too large.
Yeah, okay, thank you.
You're welcome.
Okay, so if you have we have known, if there's no question, we thank Alice again. So okay, so see you.
Thank you for the invitation, and we encourage you again to use our software and send us your feedback. It will be very
cool. We will try. We will try. Thank you. Thank you very much.
Goodbye from Greece. Bye.